Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue talking about graphs. We've looked at a graph and we started writing some code that we could use to represent a graph. In the last video we represented the graph kind of in an object-oriented way. This is similar to an approach called adjacency lists, where basically the whole graph would be, let's call this graph 1 because we're about to make another one, would be stored as an array of vertices. So graph 1, how about it just or our shorter graph that we have here, 4. So this would make an array of 4 vertices. Of course, the problem here is we could just do this, an array dot fill of new vertex. Okay, so this would make our graph and it would be empty, and then we could put in code to add these edges so that 0 has edges going to 1 and 2 with weights of 2 and 3 respectively, etc. So just to show what that would look like, graph 1 dot edges plus equals an edge that goes to vertex 1 with, it goes to graph 1 sub 1, because we made this, the type needs to match, it's actually a vertex, with weight 2. And what have I, whoops, graph 1 sub 0 dot edges. That would add the first edge, and then, and in fact, thanks to the ability to string together plus equals, we could just type this once, have the edges, so we add one edge that goes to 1 with a weight of 2, one edge that goes to 2 with a weight of 3, and we could have similar lines that set up the edges coming out of 1, the edges coming out of 2, and the edges coming out of 3. So that is one way to represent the graph. A second way to represent the graph is using something called an adjacency matrix. Now, the adjacency matrix is in some ways much simpler and much shorter. It turns out that there are advantages and disadvantages to each. This approach of using what's basically an adjacency list only keeps values where there actually are edges. The adjacency matrix fills out a full matrix, so it's a two-dimensional array. Or how about I call it graph 2. And graph 2 is going to be equal to an array of arrays of integers. Okay? And it needs to be square so that every row in this is going to represent a vertex, and the values in there are the weights of the edges to the other vertices. I'm going to assume here that all of our weights have to be positive. If this were a non-weighted graph, then instead of being integer values in here, I could simply put in booleans. So you'd either get yes, it goes there, or no, it doesn't. With weights, you just have to specify there is some value that means that there is no edge. Depending upon the nature of the problem, that might vary. You could wind up doing something like, in some algorithms you want kind of an infinity, so you'd probably, if it were ints, you'd use int.max value to represent an edge or a connection that doesn't exist. But let's see this. I'm going to use 0 in this case because we only have positive weights in this graph. So vertex 0 does not connect to itself, so I'm going to put that in there. In the next slot, this is its connection to vertex 1. There was a weight of 2. In its connection to vertex 2, there was a weight of 3. And it does not connect to vertex 3. There is no connection directly from 0 to 3. Comma. And what I want to do is copy that, paste, paste, paste. This has to be square, so I need the same number of rows and columns. All the diagonals are going to be 0 because nothing connects to itself directly in this graph. In a digraph, it is possible to have a vertex that has just a loop coming off it and connects directly, but none of mine do. So vertex 1 leads to 2 and 3 with weights of 5 and 4 respectively. So 5, 4. It does not go back to 0 and it does not lead to itself. Vertex 2 only has one outgoing edge. It goes to 3 with a weight of 2. So it goes to vertex 3 with a weight of 2, and then our last row across here, vertex 3 only connects back to 0 with a weight of 1. So that's a 1, that's a 0, that's a 0. So the entire information for that graph is contained in this one little matrix. As you can see, this is a much smaller representation. If this were a non-directed graph, then edges would basically go both ways, in which case this would be symmetric across the diagonal. So the 2 here would have to be mirrored by a 2 here if the arrows didn't have directionality, if your edges were non-directional. One downside of this, if I had a large number of vertices but relatively few edges between them, this array is still going to have order n squared elements in it. But I wouldn't need order n squared elements. I'd only need order n if the graph was relatively sparse. So there would be memory overhead. But as long as your graph is fairly dense and you don't have a lot of additional information, for example, this wouldn't work so well for things like rooms in a maze, but for most of the problems that you run into with graphs, a simple representation like this is quite sufficient. So now that we've seen this as an alternate way to represent it, we're going to come back in the next video and we're actually going to start writing some algorithms that will use a graph, and we'll write it so it uses the graph in this format here using the adjacency matrix.